In this video, I am focused on angled forces and rotated coordinate systems. This is the second of 7 videos in my Unit 3, titled Dynamics in One Dimension. If you want to practice what is covered in this video, then check out the video description. You can find a link to my worksheet 3.02, as well as video answers for each problem. Let's start with an example force diagram for a motionless object. 3 forces simultaneously act on the object, and the goal is to write equations in each dimension that explain why the object is not moving. What some students try to do is to include all 3 forces in the same equation, like this. But this is a wrong idea because of a directional problem. F1 is directed along the x-axis plane, F2 along the y-axis plane, and being that F3 is angled, it is acting in each plane at the same time. Forces, like all vectors, cannot be compared in the same equation if they act in different dimensions. So if this is the wrong idea, then what would be a better idea? What we want to do is to draw in components that visualize how much of vector F3 points in each of our 2 dimensions. F3x shows how much of F3 points to the right, and F3y shows how much of F3 points upward. Now I can write my dimensional equations, comparing the leftward F1 to the rightward F3x. They are equal, and that would explain why there's no motion in that plane. And F2 downward is balanced by F3y upward, and that would explain the lack of motion in the vertical dimension. Notice that the overall value of F3 is not included. I use that up to get my components, and it is the components that go in the equations. Let's look at an example. Here we have 2 ropes that are tied to a box that hangs at rest. The goal is to complete a force diagram for the hanging box. I start by identifying my object, and then completing the diagram. I have a downward force of gravity from Earth. The horizontal rope provides tension force to the right, and the angled rope provides a tension force up and to the left. If you have multiple forces that are the same type in the same diagram, consider using subscripts to make them stand out. So I'll call the up and left force Ft1 and the rightward force Ft2. From here, it is Ft1 that is angled. So I want to draw in my components. Ft1x shows how much of Ft1 is directed to the left, and Ft1y is how much of Ft1 is directed upward. As I write my dimensional equations, I compare left to right and up to down. So Ft1x is balanced with Ft2, Ft1y is balanced with the force of gravity, and these explain the lack of motion in each dimension. Let's look at another example. Now we have a box that is again tied by 2 ropes, but both of these ropes are angled. I start by identifying my object. I complete my force diagram, where there is a downward force of gravity, and again 2 tension forces, but each of these tension forces are angled because of the angled ropes. Because they are angled, I will draw in the components for each. Ft1x and Ft1y are directed to the left and upward, respectively, and Ft2x and Ft2y to the right and up, respectively. Now I can write my dimensional equations. I am again comparing left to right and up to down. Ft1x is balanced with Ft2x to explain the lack of horizontal motion, and the 2 upward forces, the 2 y components, should be added together, and they are balanced with the downward gravitational force to explain the lack of vertical movement. Next, let's look at a situation that involves an angled ramp. We're looking to draw a force diagram for this block that is at rest on the angled ramp. I have 3 forces that act: a downward gravitational force from Earth, a normal force that is directed up and to the right, perpendicular to the ramp's plane, and then a static frictional force directed up and to the left, parallel to the ramp's plane, and preventing the object from moving down and to the right. Before we make any equations, recognize that only one of our forces lies on the xy plane. That's the downward force of gravity. And 2 of our forces are angled with respect to the plane. That would be friction and normal force. This is what angled ramps do. They tend to produce a lot of angled forces. Here again is the force diagram compared against a standard xy plane, and because 2 of the 3 forces are angled with respect to the plane, this will be a challenging problem to analyze. Fortunately, there is a tool that we can use to help with angled ramp problems, known as a rotated coordinate system. And what I'm going to do is rotate the x and y coordinates behind the force diagram. Normal force is perpendicular to the ramp's plane. Friction is parallel to the ramp's plane. So naturally, there is a 90-degree angle between these 2 forces. If I were to rotate the coordinates clockwise to align the normal force with the y-axis, Well, naturally, friction will fall on the x-axis because these forces are 90 degrees apart. So I went from having these forces be angled with respect to the planes to now in line with them. So analyzing these two forces will be easier. Unfortunately, gravity, which used to be in the y-axis plane, is now angled with respect to the rotated plane. So this force is more challenging to analyze. However, in the grand scheme, I think the analysis got easier. Two forces have improved, and one force got harder. The next thing to do is to analyze motion. If the object is going to move, it is going to move parallel to the ramp's plane, down and to the right, or up and to the left, in this example. Because of which, the object will be moving in 2 dimensions at the same time when compared against the standard plane. But now looking at those motions compared against our rotated coordinate plane, observe that the object will only move along the x-axis plane, and it will have no motion along the y-axis plane. This will make the problem easier to analyze, and is another reason why using a rotated coordinate system for an angled ramp problem is a good idea. Let's now analyze the force diagram against our rotated coordinate plane. It is the force of gravity that is angled and therefore requires components. So I have drawn an FGY and FGX respectively to show how much of the force of gravity is directed in each dimension. Now I can write my equations. The reason the object is not moving along the rotated x-coordinate plane is because static friction up and left is balanced with the force of gravity's x component down and right. And the reason the object is not moving along the y-axis is because the normal force is balanced with the gravitational y component. Now I can introduce rotation step number 2, which is about breaking the force of gravity up into its components. I could have drawn the force of gravity x component first here, and then closed the triangle with the gravitational y component here. But I would recommend you do it in the way that is shown in the image. Notice that I have drawn the gravitational y component along the negative y-axis and opposite to the normal force. I think this makes solving the problem easiest and will help us get the ramp's angle of incline involved. Most angled ramp problems will provide the ramp's incline angle, the one that I am pointing at in the picture on the left and that I have set equal to 30 degrees. On the left, we have the original xy coordinate plane, and on the right, we have the rotated one. Here I am putting them on top of each other, and I want to point out that the original x-axis, the horizontal green line, is parallel to the base of the ramp, and the rotated x-axis, this slanted red line, is parallel to the slant of the ramp. Well, if there's a 30-degree angle at the ramp's bottom right corner, then I would argue this up here to be a similar triangle and also a 30-degree angle. I'm showing this because it looks like to rotate the green axis into the red one, we would have to rotate 30 degrees, and therefore, that is how much we need to rotate everywhere. Comparing this against our force diagram, the force of gravity downward is a lot like this green axis line, and the force of gravity y component is a lot like this red axis line. If it's 30 degrees between these on the left, then it would also be concluded to be 30 degrees between the force of gravity and the gravity y component. So now we can talk through rotation step number 3. If you did the first 2 rotation steps mentioned, then now you can use the angle of the ramp's incline between the force of gravity and the force of gravity y component. Here I wanted to summarize what has been discussed so far. You are likely to run into angled forces when you solve problems, but you don't always want to rotate your coordinates. So when should a rotated coordinate system be used? If you are running into angled forces and they are not part of an angled ramp problem, then I would recommend you use a standard xy coordinate plane and just break up the angled forces into their components. But if instead you are running into angled forces and it is an angled ramp problem, then I would recommend you rotate your coordinates as it will make the problem easier to solve. Let's end with an example problem. Here we have a person pushing a block parallel to an angled ramp, but it is too heavy and does not move. Question A is about completing a force diagram for the motionless block, including dimensional equations. And question B is about labeling where the 25-degree ramp angle would appear in the force diagram. If you want to pause the video and try this problem on your own, resume when you are ready, and I will talk you through the solution. First thing I want to do is identify my object, which is the box. From there, we draw the force diagram where there are 4 total forces. We have a downward force of gravity from Earth. We have a pushing force from the person directed down and left, parallel to the incline. A normal force directed up and left, perpendicular to the incline, and a static frictional force directed up and to the right, parallel to the incline and preventing the object from moving down the slope. Because this problem contains an angled ramp, I would want to use the 3 rotation steps mentioned earlier. Notice how I have aligned the positive y-axis with the normal force. I have drawn the gravitational force y component directly across from the normal force and along the negative y-axis, and now I can label the ramp's incline angle of 25 degrees between the gravitational force and its y component. So I've already answered question B. To finish question A, we need those dimensional equations. So I want to compare all the x-axis forces against each other, and as well the y-axis forces against each other. Along the x-axis, there are 2 forces that are trying to make the box move down and left. That would be the pushing force and the gravitational x component. There is 1 force resisting that, the static frictional force, and I want to say that the push plus the gravitational x is balanced by friction to explain why the object is at rest in this plane. In the y-axis plane, the box is motionless there too, so the normal force up and left should be balanced with the gravitational y component down and right. If you found this video helpful, then please consider hitting the like button and subscribing to my channel. You will help me reach more students. For more content videos, tutoring information, practice materials, and live review sessions, check out my website or follow me on my social media platforms.